one problem, the quiz on Monday. So we have given file for table. It's different from the question 1. So suppose that the block size is 512 byte and the pointer address size is 6 byte and record pointer is also the address size is 6 and the number of the record is 30,000 and also it uses the fixed line and the unspent. Then A. So calculate the total number of data blocks. B. How many blocks we need. And the index entry size. Index entry size is a keyword, the plus, key plus the address size. And the index blocking factor. Sometimes it's called the fan out. The blocking factor for index block is called the fan out, so or the FO. So it's the same thing. So why don't you calculate these three first? Using those information. So we have a file is ordered by the social security number. By the way, to calculate the index entry size, the key is the social security number is 9 byte. Okay. So we have primary index on SSN. At the time, calculate the number of a first level index. So how many index key entry we need? It's a primary index. Then calculate the first level index block. It's a single level. How many blocks we need? On the primary index is a sparse index. So you need to count number of blocks for the table file. How many blocks? Because we are going to select one key from the data block. Then using this index key entry, create the index block, how many blocks we need. It's the same as the data block, what we have done in the data block question number 1. So how many index blocks? Then the using binary search, the select the employee using social security number. Then how many blocks we need. if you understand the structure, data structure concept, the calculation is not that difficult. Please try to solve the problem by yourself the first, okay? If you see the answer, it's very easy to calculate. So A, so how many blocks do you need? How many blocks?
7,500.
7,500. So A, so number of blocks. So to calculate the number of blocks, we need to know the block size. Block size is 512 bytes. So this is a block size 512 bytes. And how many? What is the record size? Record size is
150.
100. We can add up all of this. So this is 115. So how many for the record in one block?
4.
It's 5 is not, 4 is possible. So, but it's unspent. So for blocking factor for the table is the 4. So which means the 4 record for each block. So how many blocks we need? It's 3,000 divided by blocking factor. That's 7,500. 7,500. Okay, good. Then the next one is the index entry size. So index entry size is the social security number, size of the social security number, plus size of the address is the 6 byte pointer size. So 9 plus the 6 is the 15. So indexing the key entry, the index key entry size is 15. Then we can calculate the buffer factor for index. So how many index key entry for 512 bytes? So 512 bytes divided by 15. How many of them?
34.
It's exactly 34.
34.1.
34 point something, right?
Yeah.
So that should be the floor because it's unspent. So part of the index key entry will be max block. So this is 34. In other words, so if we draw the diagram, this is a data file. Employee. How many? 4 of them. And how many? 4 of them. So total how many block? It's 75,000 in that data file, the block. Then if we create the index, so we can select this one are we do not know how many, but the index key entry is 15. So how many of them is 34. So we can have the 34 index key entry in one block. We don't know yet how many index block we need. Okay, so that is A. Then B, we have primary index. Primary index is useful for the key ordered file. This file is ordered by social security number. So like the social security number is here. So social security number. This is order. So we don't have to index each and every the social security number in step 1 or each block like this. So index. Then how many index key entry? So same as number of data block because 1 index per block. So total 75,100 the index key entry we need. So L in the B, L 75,000 index key entry. Then calculate the how many blocks. how many blocks we need. So index blocking factor is 34. So 34 per block. Okay, so total we have the 75,000. So 75,000 divided by 34. So this should be ceiling or floor. When we count the block, always ceiling. Because even though 1 byte is used, then entire block is needed. So this will be block how many? This will be 220 something. So 221. The block we need. So which means 34 index key entries. 34 index key entry total how many blocks? 221 the blocks we need. This is the index of the employee. This is the employee table data structure. Okay. Then the B3. So we are going to process select from employee and where the SSN is equal to 1, 2, 3, 4, 5, 9. Even though we do not talk about the query optimization, query processing, query optimizer yet, so intuitively we can understand there are different ways to access this data file. First approach is, as we have seen in the question number 1, so we can use, because it's ordered, we can use binary search directly. Okay? So you can calculate how many blocks we need, log to number of index. So if you calculate this one, and we have the number, maybe 2 to the power of 10, and 3 is 8, so 2. So it's a 12 something, right? So which means it's a 13. I don't know the exact number, but roughly it's a 13 blocks are needed to access, to find the data, the employee using social security number, using binary search. However, B3 asks if you are using the primary index, this one, how many blocks we need. So if we are using the index of this, so this one is all index are sorted. So we can use binary search to find the 1, 2, 3, 4, 5, 6, 7, 8, 9. So which means log to relation to how many? 221. So this one is going to be 7.79 something. So this one is the floor or the ceiling. When we count the block, it's always ceiling. Okay? Entire block we need. So 8 blocks we need. Only for index. So always we need to count plus 1. So 8 plus 1. Plus 1, plus 1, 8 plus 1. 9 block is needed. So which means using binary search we can find the specific index block. And using this pointer, we can access the data file, social security number, 1, 2, 3, 4, 5, 6, 7, 8, 9, employee. So how many blocks we need? 9. So later we will discuss about what query optimizer is doing. Query optimizer will select this one or this one. Second one, using index is faster. So we are going to select this approach to access the data. That's what query optimizer is doing. Number 6. So we have another index. It's a secondary index. First, the secondary index is dense index or non-dense index. Always dense, non-dense. Secondary means this is a primary index. Secondary means it's not sorted. So we need to index each and every the record. which means it's gonna be dense index. So dense index, so how many index key entry do we need? Same as record. How many record? 30K. So we need 30,000, the index key entry. Okay, that is the B1. So a C1. You can change it. The question number C1 is 30,000. Then calculate the number of first level index block. Index, the buffering factor will not be changing. So what is the buffering factor? It's 34. So which means how many blocks we need? We can calculate the B. This is a secondary index. So 30,000 divided by the 34. Okay, right? So how many? 882 point something. So it will be 883. So we need more index block than the primary index. Why? Because primary index is a sparse index. We need the one per each block. So we need the total 7,500 index key entry that need the 221 block. However, on the other hand, secondary index is the same number as the record, which means we need the 30,000 index key entry. So we need more the index block. So how many? 883. Okay, so we have the 883 index block. So when we are using the, for example, if the social security number is secondary, it's not sorted on the data file. At that time, we can use secondary index log. How many? 883 plus 1. So 883 is 2 to the power of 9, right? So it's a 9 point, I already calculated this one, plus 1, so it's a 10, plus 1, total 10, average, the index access, index block access, then plus 1, so 10 plus 1, total we need 11. Still, this one is faster than the without index, okay? So this one is faster than, no, 13, so, okay? Secondary index is faster than the without index. But the best one is if we have primary index, this one is faster. Okay, questions? Please try to solve the problem by yourself. The calculation itself will not be difficult. It's not difficult, but if you understand the concept data structure of index file and data file. So during the exam, I'm going to allow to use calculator, but not cell phone. So, but without cell phone, you can actually calculate the log based on 2. It's 2 to the power 10 is 1024, something like that. Any questions? Okay. And I didn't explain the each and every evaluation over here, but you can try to. I already put such an evaluation on the slide, so please try to. So for example, this one is example 2 level primary index. In case of 2 level, so we can do the same thing. For the fan out means is the buffering factor for the index block. So first level and the second level, third level, like that. So you can calculate each level and add on. So always you need to count the plus 1, the data file, the plus 1. Okay. Then yes, the one day we talk about the B3 index. So B3 index, idea of the B3 index is a balanced tree. So because search tree can be skewed. In case of a skewed the search tree, the extreme case, the search tree will be the same as the linked list. So we cannot get the full benefit of a tree. So to address that problem, So idea of the balanced tree is, so such tree growing top to bottom. So from like a family tree, ancestor, so parent created child. Parent, because of that, sometimes your aunt may be younger than you, right? It may be possible because it's growing top to bottom. So it's not balanced eventually. So two other steps. Why don't we create the tree bottom to up? So to do that, so problem is if we have unlimited node, the block size is really huge. We can keep all together in one block. That's not possible. So in case of full, so we cannot insert the data index key entry. We are going to call such an event situation as full of node. In case of full, idea split. Okay, you can create a sibling node. So let half the left-hand side node, another half second half the next right-hand side node. However, we need to separate them, delimit, branch. So we can select the middle value as a parent. So we are going to select the middle value as a parent, which means we can make the tree grow bottom to up. Always the same level as the node. That is a B3 index. So quickly review the B3 index that we have done the last time. So that is this one, example. So we have the 8 by the 173 12 9 6. Okay, so this is our the index key entry. As I said, when we insert the data 8 is not the only data. So 8 is the ID. It's a key, index key, and the lead, and the major, and other information. But to simplify, so we are going to consider the only index key entry. In real situation, data file is A, lead, and the CS and all information will be inserted as a record of the table. Then the index A, then the pointer address, then point at this address like this. So we are going to simplify to insert data using only the index key entry. And also the index has order P. Order P means, so if we illustrate the order, this is a node structure. Why don't you remind that you have done in the data structure class binary tree. Binary tree is like this. The left-hand side, right-hand side is the value, and less than this, going to here. Right? Bigger than this, going to here. So similarly, this one has the children pointer. So point the children node. And we have index key entry and data, the pointer. So point the data, and this one is another one, A2. So in case of order P is equal to 3, how many index key entry? 2 of them. This means blocking factor for the index. In other words, the fan out is the 2. So this is our node structure. First, you need to decide the node structure. In case the order is P, order P is equal to 4, this will be like the, how many index key entry? 3. So order P minus 1, so 3 of them will be inserted like that. Okay, so we are going to use this one because order P is equal to 3. So let's start to insert the 8 first. If you do not have any index node, instantiate. Create the first one. So that will be in real situation. So real application, real DBMS. So instantiate this one means allocate the index block from the data file. So file system. So we are going to use a table space as the space of your database. Like the MySQL use the database name and Oracle create the table space. That space has a number of the block like this. We can allocate the one available block to this one. And the structure of that node, index node is like that. So we have 2, p minus 1, the 2, the key entry. So 8 will be inserted. 5 will be inserted. So after insert the 5 and 8, so it will be like this. Don't forget, there is a pointer, there is a pointer. The solid one, it has a pointer to the data file. For example, this one point is, and this one point is like this. Then eventually we are able to access the data. Then 1 is inserted. So in case of full of node, idea is first decide the middle value. So 1, 5, 8. So decide the middle value. Based on the middle value, split. Then left hand side and right hand side. Then allocate the left hand side and the right hand side. The last step is the middle value will be promoted. The promotion means going to promotion to the parent, which means it will be parent node. So in this case, the middle value is the 5. So 5, based on the 5, we have another index node. So left hand side is a 1, right hand side is a 8, and the middle value will be promoted. There is no parent node, so we can allocate, create the new index node, same data structure. So 5 point this, and 1 point data block, 8 point data block. Plus the last step is we can check the pointer, index pointer. So this one less than 5, go to here, bigger than 5, go to here. Then it's a balanced. Level 1, level 2. Always the level 2 or 1 less. Then 7 is inserted, we need to, it's the same as the search tree, find the node where the 7 is inserted, the 5 and the 8. Actually it's a search. So 5 and bigger than 5, there is a space so we can insert 7 and 8. So 3 is less than 5. Even though you have a room here, we are not going to insert the data here. Instead, we are going to find the leaf node always. So then the less than 3 here, so we have space, 3 will be inserted. And the 12 is bigger than 5, there's no space. Even though we have space here, we are not going to insert the 12 here. Instead, we are going to find the leaf node because our goal is to balance. Always find the leaf node, search the leaf node where the inserted data will be in. So, no space. So this one is a full. 7, 8, 12. So which one is the middle value? 8. So based on 8, so we are going to create a new node. So middle value 8, the left hand side is 7, right hand side is 12, and middle value will be promoted. There is a space. The parent node will be used for the promoted the middle value. So then check less than 5, bigger than 5, less than 8, and the bigger than 8 goes to here. So this is up to inserting the 12. Question? It's just a simple algorithm. That is one of the benefits of using binary or balanced tree. Okay, 9. 9 is supposed to be inserted here. Oh yes, we have space, so no problem. Then the 6. 6 will be inserted bigger than 5, less than 8. So going to here, so we have a space. It's a 6, 7. Okay. So this is a balance tree, like this. One more step that we have done. Let's insert the 13. So 13 supposed to be here, right? Bigger than 8. So there's no space. So it's a full. So 9, 12, 13. So in case of full, find the middle value and the left hand side and right hand side. We need to create the allocate the index block, and 9, 12, 12 will be promoted 13. Then the promote 12. There's no space. The in parent node, same process. In case of 4, 5, 8, 12. So 5, 8, 12. So find the middle value 8. Left hand side 5 and right hand side 12. And middle value will be promoted. Promotion create a new index node. So this will be 8. And check the pointer. Less than 8. Bigger than 8. Less than 5. Bigger than 5. Less than 8. So this one. Don't be confused. Sometimes it's even though you have a space, you cannot use because it's a split from the parent node. So bigger than 8, less than 12 goes to here. Bigger than 12 goes to here. So this is the index of the after inserting the 13. So in real the implementation, you are going to allocate, okay, the available block for each. Then each block has the block ID. Like this one is a 0, this one is 2, 4, 5, 10, 11, 13, and 20, like that. So using the block ID, it will be used for address of the pointer of the index node. So like the 0 will be here, and this one is a 4 and 2 here. So you can implement the index structure using such a file system. Question?
So can we keep 7 beside 5, sir?
Where is the 7, 7? Yes.
Beside 5 only can we keep?
So bigger than 5. Okay. 7 is not promoted. 5 was promoted, that is the reason is here.
Yes, sir. If we keep 5 and 7, the middle one will be 6 or no? 5 greater than 5, less than.
So bigger than 5, but less than 8. So this side all less than 8. Okay. That's the reason we can keep the order of the index. Okay. So for example, when you insert the 4, even though we have space here, we are not going to use, because we should keep the balance. So always find the block. So where the inserted data will be in. So that is the 4 will be here, but there is a 4. Then split and promote the middle value. Then this one will be used for the promoted the middle value. Then keep the same method. Okay. Well, question? When you select, so let's say this is the EMP from employee EMP where ID is equal to 9. How many blocks do you need to access? How many blocks? 9 is 1, 2, 3, and 4. So 4 blocks. So you can compare with the primary index and the secondary index. So using B3 index. Okay. Then, what about the 12? How many blocks? 1, 2, then using this one, 3. So 3 blocks. What about 8? 8 is the 1, 2. So, B3 is balanced. Okay? As you can see, the B3 is balanced. So it provides upper bound maximum number of the block ion. So you can see the maximum is the level plus 1. Level plus 1. So this one is less than level plus 1. The B3 guaranteed maximum. However, it's not really in terms of index key entry. Sometimes level 1, sometimes 2, sometimes 3. So extreme case. Think about the extreme. What if you have the 10 billions of index key entry? It's huge. You can calculate based on the considering the order. So it will be sometimes 100 level, 200 level. Really huge tree. So if you access the fortunately the access the data from the root to ion. However, leaf node 100,000 plus 1. So even though B3 itself is balanced, but when you access the data using index key entry, it's not guaranteed. It's only provide the upper bound. So in other words, when you travel to the Manhattan, like for interview, so Christopher would like to use the train. Train guaranteed the 1 hour 10 minutes to the 1 hour 15 minutes. But if you have transportation, so sometimes takes the 10, but no longer than 10 hours. So guaranteed equal or less than 10 hours. So if you are lucky, 1 second. I don't know how to, but if you are not lucky, it's a maximum full. The period is 10 hours. So are you going to use this transportation for your interview? It's not safe. If you are lucky, so if you arrive the 1 second in Manhattan, you need to spend the time for 10 hours. It will be exhausted. So what you need from the query optimizer point of view, DBMS administrator point of view. So it is better than the search tree, like the multi-level index. However, still it's not guaranteed how long it takes. We need, even though it's slightly the longer than the transportation, train is always the 1 hour 15 minutes to go there. Then we can schedule. Then I can be ready with the perfect the condition like that. So we need such a train, so transportation. So we are going to make the really balanced. Really balanced means all index key entry has the same level, same ion. How can you make that? What is why the B3 index causes such a problem? Sometimes 1, sometimes n. It's a promotion. Because we promote the middle value. So eventually, one of them will be good. And if you have the order 10, we have the 10 of them in the root node. But the other, sometimes here, it's because of promotion. So why not? Instead of promoting the entire value, keep the middle value in the either left or right. Okay? Still keep. Then only value will be copied. For example, if the 12 is promoted, so 12 is still here. And copy the 12. So this 12 is the real index key entry. Then this 12 is not index key entry. It will be used for what? Split. The branch condition. Left and right. So idea is, why don't you put down all index key entry to the leaf? Then we can have the same level. Same level. Okay? Always the 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is called the B plus 3 index. So B plus 3 index is almost the same as the B3, but it's B plus 3 is really balanced. So we are going to see how to create the B plus 3. Before we start, B plus 3 is used in almost all relational database management system. So 90.99, okay? The relational database management system the even real the database that you design or some other company design, when they create the index, it's a B+3. Also, B+3 is not only for the database. It's mostly used in the database index, but it not just was, it has been used a lot of data structure that require indexing. One of the popular example is what kind of the file system are you using currently on Windows 10? NTFS? So most of you guys use NTFS. Before NTFS, so what did you use? 32? FAT 32? And before 32, FAT 16? FAT used B3 index, B+3 index. For indexing what? 5, the block. Okay, so 5, the FAT 16, FAT 32, it used such a, but it's limited by the size, like the 4 GB and so on. Then NTFS address such a problem. Also, a lot of the data structure that need indexing, they are using B+3 index. Why? It's so simple. We spend less than an hour to understand the B3 and the B+3. And the easy to implement performance is really good. So that is the B3 and the B+3. So we will see the B+3 index. Before we start, question. When we have order P is equal to 4, okay? So how many index key entry? 3. So when you insert the new data, let's say 1, 2, 3. So we have the new data 4. It's a full. So we have 1, 2, 3, 4. Which one is the middle value? 2. You can pick what?
You have to decide whether you want to always go high or low.
Yes. So it's up to you. Okay? So it cannot be 2.5. It doesn't make sense, right? So instead, you can select either this one or this one. So textbook, your textbook use the left-hand side. Okay? So highest one, the biggest one, the less than the middle value. Okay, middle value is 2.5. So from the middle is the highest one. Or you can select the lowest one from the right-hand side. So either of them is fine, but you should be consistent. Okay? So in our class, no reason just to select this one as the middle value. Okay? In your exam, please use. But always, the 1 or 2 students select this one as the middle value. So then I need to the grade again and again. Please select. It's not your fault, but for consistency, we are going to use this one as the middle value in case of even number of the data. Okay? So then, first, when we consider the B+3, so B+3, so order P is equal to 3. So we are going to decide the data structure. Once we have allocated the node, so there are 2 types of node structure in B+3. One is the leaf node. As I said, only leaf node has index key entry. So we should have like the key 1, key 2, and data pointer. Question: do we need the children pointer for leaf node or not? What is the definition of a leaf node in tree structure? Parents, but no children. So we don't need children node here to save the space. So that's the reason there's no. However, internal node means root or other, but except the leaf node. They have children node pointer 3. P is equal to 3. Then What about this one? Do we need the data pointer for the internal node? No, because we go down to all the index key entry for the leaf node. So we don't need. Instead, just K1. It's actually not K1. It's whatever. The S1, S2, like that. Okay? It will be used for the branch, the condition, not state. It's a branch, one split. Okay, split 1, split 2, like that. This one is the pointer for children. So we need the two different types of the node structure. One more thing is I don't explain this one. I will explain later after I construct the whole B plus tree. Okay, we are going to use the same index key entry value 3, 12, 9, 6. So first 8 is inserted. Which one will be? The leaf node will be created. So we need this one. So 8 will be here. Definitely 8 is pointing to the data block. Okay, so we can solve it. The next one is a 5. So 5, 8, like that. Okay. Then what about the 1? When 1 is inserted, so full. So 1, 5, 8. Decide the middle value. In B3 index, this one is promoted. However, in this, okay, this one is a middle value. Up to middle value is the left-hand side. The other right-hand side. So don't be confused. The middle value is included left-hand side. Because as I said, our idea of B plus 3 keep all index key entry in the leaf node. So, in other words, we are going to copy, create another node. 1 and 5 is here. And the other 8 is here. Okay? Then, we are not going to promote the middle value. Middle value is still here. Instead, create the internal node using this one, internal node. Then copy the only middle value. Copy. So 5 will be here. So 5 does not have data pointer. Instead, it will be used for branch condition. So meaning is equal or less than the 5. Left-hand side. Equal or less, because 5 is copied from here. Bigger than 5, right-hand side. Okay? So that's the difference. B3 index, promote, and key entry. However, B plus 3, equal or less than the middle value, left-hand side. The other right-hand side, middle value will be copied. So this one will be used for branching to left-hand side, right-hand side. Yes?
Professor, why the leaf nodes are not used in the first that you used?
The leaf node.
The first one, which
This
is
one?
used as a pointer for all, even that should be using the leaf nodes, right? Like
This one is not leaf, this one is right now parent. Okay? So leaf node. So her question is, can we use this one for the leaf node? So 3 is always the parent, child, parent, child. So, but most of the time we create the tree from top to bottom. But here, B3, B plus 3, first create the leaf. Actually, this one is when we create only one node, this one is a leaf node, this one is a root node, this one is an internal node. Okay? Because we have only one node. Then, once it is full, we need to keep the order. The index should be ordered. So, to keep the order, but to keep the characteristic of tree, parent and child's the relationship, we are going to create the parent. Okay? Then we use this one as the internal node. In this case, the root node or internal node, not leaf node. Then leaf node has the data point. So when you access one, always you need to go to the leaf node. Right? The 1 is less than 5, 1 is here using this one, access data. 5, even though you have a 5, there is no data pointer. You need to equal or less than 5 goes to here. Then 5 is here, then the access data. How many? 1, 2, 3, 1, 2, 3, 1, 2, 3. Always 3 ion. It's the same, guaranteed. Okay, then 8 done, 5 done, 1 done. And 7. 7 is bigger than 5, there's a space. So 7, 8. Then 3. This one definitely cannot be used for the index key entry. You need to find the leaf node. Less than 5. The 3 is less than 5, so it's supposed to be here. So it's a full 1, 3, 5. Decide the middle value is 3. Then equal or less than 3, left hand side. 5 is the right hand side. So we are going to create the new node. Like that. So 1, 3 is here. And the 5 is here. Then 3 will be copied to the parent. So which means insert into here. So there is a space 3 and 5. Same thing, reorganize the pointer. Equal or less than 3, this block. Bigger than 3, equal or less than 5, goes to here. And the bigger than 5, they're here. This is the B plus 3 index. So when you access the data, 1, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Always a 3 ion. Because the leaf node has the data point. Then 12. 12 is bigger than 5. Okay? So supposed to be this one. It's a full 7, 8, and 12. So which one is the middle value? 8. So equal or less than middle, left hand side and right hand side. So we can copy. This one is 12. Then insert, copy 8, which means insert into the internal node. This is a little bit tricky part. So 7, 5, 8. Which one is the middle value? 5. Okay. Then do I keep the left hand side here or only 3 as the left hand side? So number 1, 5 is 3, 5, and 8. 5 will be here. Or 3, 5, and 8. Which one? Second one. Because internal node is the same as what? B3 index. It's very similar as a B3. We don't have to keep. The reason why we keep the middle value here is we try to put data pointer in the leaf node. However, these are not leaf node. This one will be used for split. So in this case, we are going to follow the same procedure as the B3. It's tricky. So this one is the middle value, and this is the left hand side. This is the right hand side. So three will be here, 5 will be here, and the 8 will be right hand side. 5 will not be copied in the left hand side. So check the old pointer. Less than 5, bigger than 5. Less than, equal or less than 3 is here. Equal or less than 5, bigger than 3 goes to here. Don't be confused. 5 based on 5, equal or less. Then the bigger than 5 equal or less than 8 goes to here. Bigger than 8 goes to here. Then when you access the data 5, but this is not the data pointer, equal or less than, then 1, 2, 3, 4. And 12, 1, 2, 3, 4. Or any data point, the index key entry require 1, 2, 3, 4 I. So it's really balanced. Okay, what about the 9? 9 will be bigger than 8, bigger than 5, bigger than 8, so 9 goes to here. And the 6, bigger than 5, okay, and the less than the 8 goes to here. Even though we have the 6, it doesn't look like the problem, but it's actually a problem because it's equal or less than 5. There's no way to find. Instead, you need to insert the 6 over here. So split into 2 and copy the middle. Okay, so this one is once you split the 6 and 7, 8, select this one. So B plus 3. Okay. One more thing. I didn't explain this one. This one is called sibling pointer. Sibling pointer means it's a point next one. Next one. Next one. Like this. Then, question. Why do we need the sibling pointer here? Why?
You can access the next index values from that point.
For which case? This, for example, select from employee ID where ID is bigger than 1, for example, equal or bigger than. This is called what? Range query. When you access the data range. So, for example, let's go back to the B3 index. So this is a B3 index. So, I'd like to access the ID is equal or bigger than 1 using index. How can you? Please follow. First, read this one, goes to this block 1 and 3. Then, what about the next? We don't know where it is. You need to always go up. Because of 5, you cannot jump. Always, it's a up and down, up and down. That is the way of search in the tree structure. You probably remember. Tree is, you need to check the leaf and going back. Back propagation. You need to back propagate in and up and down, up and down. So, 5 and the 1, 2, 3, 5 and the down and up, down and up. If you have the level 10, how many cases? Really big cases, up and down. So, this one does not provide a good performance for range query. However, B plus 3, because we put down all data index key entry to the leaf node, right? They are already sorted, right? You can see 1, 3, 5, 6, 7, 8, 9, 12. It's sorted. So instead of up and down, we can just point the next one. So don't forget to create the sibling pointer. For your reminder, in your data structure class, CS 102, right? CS 102, the CS 102, sophomore. You should take the data structure class. So in the tree structure, how can you use the tree structure for sorting the data? In the binaries. Yes, how can you? Left, middle, right. What? Right, middle, left. Like that. Which means up and down, up and down. But B plus 3, you don't have to. So it provides a really good performance when you are using range query, using index. Okay, so this is called the sibling pointer. So this is a B plus 3. This B plus 3 is exactly 99.99% the same as the real B plus 3 used in the relational database MS system. As you can see, simple, it works well. There is one problem which I don't explain. B plus 3 and the B3, both of them have the problem. I mentioned about always insert, right? Insert. What about the delete the data? What happens when you delete the data? At the delete 7, delete 8. You need to merge. So this one is okay because we have only 2 index key entry. So suppose that the index delete the data, you need to check. So insert, you need to check full. The delete, you need to check what? Merge. So you need to merge when you delete the data. If capacity is less than 50%, how? You can merge with what? Sibling. Because you have a sibling pointer. So you can merge. Then consequently you need to change the parent node. But this is not simple. So I'm not going to explain in this. Even the textbook doesn't mention about the details of the merge, but the merge can be used in case of a delay. Okay? So that the B plus 3 is done. So B plus 3, when I taught the only graduate student, this is a good example of the project. So implement the B plus or the B3 index. So how can you start to implement the indexing structure? First, you need to implement the data structure, data file. So create table space, your database space, based on file system. So you can create the simple file-based file system. Then use this one as the table space for table and index based on the block. So whenever you insert the data for the data, you can allocate the block and create based on block size, record size, and the buffering the blocking factor. For the index, the table is simple. You can allocate and insert, allocate, insert. When you create the index, your main driver, so if you are using Java, the main driver should have the algorithm of this. Then you can create a class for each of them, the leaf node and or the internal node. So if you are taking operating system, you will see what is a file system and how to implement a file system. So file system has basically 2 parts. One is memory structure. Always, any file system has the memory data structure. Why? First, speed, performance. Instead of writing a data directly to the hard disk drive SSD, we are going to write the memory. So that is the reason if you plug in the USB drive, always save remove. Right? Why? Your change update is on the memory sometimes. It's not applied to the hard disk drive yet, or the SSD yet. So you need to safely remove means to synchronize the memory change on the memory to your file system. Similarly, when you implement this one, so file system, you need to define the memory structure. Then that should be synchronized to the persistent disk structure. So database is the same thing. Such a change, insert, update, or change of the index will be done first in the memory, then synchronize to the file system table space, block by block. So that will be the way to implement the indexing structure. Really fun. Painful, but you can understand operating system and the database, algorithm, and also data structure. Really a lot. Okay. Then also you can evaluate the performance using this one by following. I'm going to skip this part. If you are interested, then please go over such a thing. Okay, so that's it. Then chapter 17 has the additional part. This is called practical database design and tuning. But it's out of date, so I'm not going to use this one. But instead, I'd like to give on the last of time, the 5 minutes, I'm going to give the idea of the database tuning. So in database, there are two parts of tuning. Tuning is always the important part. Why? Because the main reason why we are using the computer system, computer resource, is always to speed up finding the information that you want. Then the processing will be added, so on. So to make your system faster, the database needs the two parts of the tuning. One is your query. SQL should be optimized. So SQL query is yourself when you code. So you need to think about what is the best performance your query. However, even though your query itself is the SQL is a good performance, if the system itself is slow, so you cannot get the full benefit of the computer resource to access the data. So system tuning, database system tuning. So there are two parts. One is the application, SQL tuning, and the second part is the system tuning. And what database, the management system tuning. Who is in charge of the SQL tuning? Developer. Mostly developer. What about the system? Database administrator. So database administrator should know your system. Then when you tune your system, it starts from hardware, computer. If your computer resource is not a good performance, no way to improve the performance. So you should have enough computer resource. Network is the same thing. Even though you optimize the data, information, everything, but if a network is using the 100K the bandwidth, so will be latency. So always check the bottleneck and such a latency of your system, infrastructure. If everything is okay, then operating system should be tuned. Operating system is because the DBMS is the application running on top of operating system. Your operating system is not a good performance, no way to overcome such a thing. So your hardware, then the operating system. Who is in charge of such a thing? Mostly system administrator or Unix administrator. Nowadays, cloud service vendor, they claim these you don't have to worry about. Fully managed by the cloud. Such a service fee will be included when you pay for the cloud. So that's good news for the developer or the company, but as a computer science student, it's a high or the less opportunity to know about such a system level and operating system level. Okay, even as you realize, some of such courses will be less and less offered. Right? So, but I believe that as a computer science major, you should know the performance of the hardware and operating system level and network level and so on. Then finally, you can think about the database. So when you tune your database management system, most important part, memory. Okay, if you have less memory, so no way. Okay, so you are going to use the buffer or for example, Oracle suggests at least half, 50% of your memory system, the operating system, and the system memory size will be should be allocated to the database, the buffer, which is called the SGA, Shared Global Area. So it's a buffer area. So for example, if you have the 16 gigabyte, the hardware, the memory hardware, so 8 gigabyte should be used for the reserve. Okay, reserved for the database. Then the memory is the first thing. Second thing is I/O distribution. The database has a huge I/O, huge number of I/O. So the I/O will be bottleneck. So you should understand how the input and output I/O is working in operating system. Simply starting from what? CPU instruction and interrupt. I need the data. Then the interrupt your operating system, send the signal to the disk controller through the what? The bus. Then this controller receive the request and convert the integer I to the low level address. Then read the data and stop, interrupt your operating system, send it back to where? Not CPU, memory. Okay, sometimes you can use the direct access memory, DMA, to speed up, bypassing the CPU interrupt. Then finally your CPU, which means database use such an I/O operation a lot. So it is better to distribute such I/O along your hardware, like the disk controller. So for example, this is a hard disk drive. So when I ask the student for advising, if all students in one room, it will be bottleneck over here. Instead, if I distribute by the grade freshman, sophomore, and junior, senior, and it can be parallel. So we can use the parallel operation for such a database tuning. So that's the overall thing of the system tuning. The last one is a SQL tuning. It totally depends on one. How to code. So we will see more about the related to the SQL tuning in query optimization. Okay? So the simple example is the huge table and small table. When you join this one, which one will be first one? Small one first, bigger one first. Small one will be, you can narrow down earlier, then find the same thing. So that's the kind of the simple idea of how you can optimize your query. Okay, so we will continue through the functional dependency and the normalization next week. So please continue to work your project. Okay, thank you, and see you next week.